Now we're going to move into the age of the 16-bit and a new numbering system. So larger numbers equals more power, right? We need to be able to compute larger numbers. But how are we going to do that? We know that we don't like having to work down in the ones and zeros of binary. Octal can still get a little bit arduous if we had to break that down too. So there had to be another system that we could put in place that allowed us to represent larger numbers that the computer could work at. All right, so let's take a large number conversion here. So I've got this laid out as binary, and let's break this down. We're going to go through this in a series of steps. Okay, ready? So if we start from the most significant bit, which is what? It's on the left-hand side, always the furthest bit on the left-hand side. So it's 2 to the power of 15. That would be 32,768. Then I go over and I see 0, 0, 0, and I go to the next one that has a 1 in it, and that's 2 to the power of 11. So now I want to add to that 2,048. 0, 0, 0. The next one is 2 to the power of 7. So now I want to add a 128 to my total. The next one is 2 to the power of 6. I'm going to add a 64. Next one is 2 to the power of 5. I'm going to add a 32. 0, 0. The next one is 2 to the power of 2. So that's a 4. And the last one is 2 to the power of 0. So I'm going to add a 1. You add all that up. Get out your calculators. Add that up. That comes out to 35,045. All right. How would you like to do that every day, huh? All right. So then we learned about large number conversion in octal. And if we went through the exact same exercise, we break it down into groupings of 3 bits. So that would be a 5, that would be a 4, that would be a 3, that would be a 4, that would be a 0, of course, and that would be a 1. And whenever you have 1 bit, instead of the grouping of 3, then it would just be 0, 0, 1. So you just append some zeros there. Okay? So this would be the octal representation. And we would represent it like this. So it'd be 104,345 in base 8. Okay, there still has to be an easier way to write these numbers. 104,000 is not a very big number, right? So we still have to come up with a better way. So how can we simplify this representation? With larger computers meant we had more processing capability. So we went to a 16-bit numbering system. All right, so here's our cheat sheet. And what we see is a 0 to 7. So if I see the digit 0 to 7, that's on the left, that's my 3-bit binary representation, right? We've gone through this. What if I change that to a 4-bit binary representation? To do that, all I have to do is add a 0 into the most significant bit, which would be the one on the left. So let's do that. All of these mean the same thing. So if I'm looking at a digit 7, which is a decimal 7, in 3-bit binary, it would be 111. In 4-bit binary, it would be 0111. All right, let's continue that. Let's go over here now and let's look at bits 8, 9, 10, all the way down to 15. And let's continue our pattern in a 4-bit binary. So if I pick up my 4-bit binary that I have there on the left, and I just put a 1 in the most significant digit, because you see I've used up all those bits, except that if I put a 1 in there, watch what happens. There we go. So these represent the bits 8 through 15. Okay. Let's just walk through a little exercise here first. So here is 4-bit binary. So if I have a binary of 1010, we know that we break that down, and I gave you the cheat sheet below it, right? So the most significant bit would be times 8, right? So it'd be 1 times 8 is 8. And then the next one would be times 4. That would be 0 times 4 is 0. So 8 plus 0. Next one would be 1 times 2. So that would be 2. So I got 8 plus 0 plus 2. And 0 would be times 1, so it would be 0. So I'd get 8 plus 2, and that's 10. So 10 is my base 10 or decimal version of that. Okay. But we said we want a single character, a single symbol. Okay, I've run out of digits, didn't I? If I look over there on the left, my digit is the same as my bit. So I went 0, 1, 2, 3, 4, 5, 6, 7. Then I went over to the right and I said 8, 9, 10. Oh, that's not a single. 11, that's not a single. Oh, crud. 12, 13, 14, 15. Those are not singles. They need to be singles. So how do I come up with a new digit system? Well, an 8 can be an 8, a 9 can be a 9. What would 10 be? I've run out of these things that we call numbers. Want to emphasize, okay, ready? Prepare your brains. Here we go. These numbers are just symbols. That's it. They're just symbols. Again, we could have put a squiggly on there and said, that's a 9. A triangle could be a 10. But instead, we put up these squiggly little characters. So that 9, if you look at that, yes, we recognize it as a 9, but it's kind of a funny little circle and then an open circle on the bottom. It's just a symbol that we've written. An 8 has a continuous flow to it. A 0 is just a big circle. A 1 is a stick. It's just a symbol. So therefore, when you get ready to see what hex does, it's just a symbol. Ready? So a 10 is an A. An 11 is a B. A 12 is a C, and so on. All the way down to 15. This is a 16-bit system. So it goes from 0 to 9, A through F. That's hex. Study this, write it down, commit it to memory. Yeah, you do need to memorize this one, guys. You need to get focused on what this bit system is because you use hex. Yeah, you do. I'm going to show you at the end of this that you do use hex, so you want to know it. All right, so let's go through a conversion process. Ready? Here's a 16-bit conversion. All right, so this time we've broken it up into 4-bit binary. See the color coding? I've got green, blue, purple, and orange. 4 bits each. Now let's do what we did with the octal before in the last topic. So we're going to do it by 4 bits at a time. So we go from 2 to the power of 3 all the way down to 2 to the power of 1. In this pattern, 0, 1, 0, 1 is a 5. It equals 5, right? You should be able to convert that by now in your head. You should be able to look at that and go, that would be 0 plus 4 plus 0 plus 1 is 5. Pretty basic stuff. Let's do the next one. Look how I brought that pattern over. Same pattern, 2 to the power of 3 down to 2 to the power of 0 for the least significant. So what is this? So I've got 2 to the power of 3, so that is 8. 2 to the power of 2, that's 4. 2 to the power of 1, that's 2. So I've got 8 plus 4 plus 2 plus 0. That's 14. Okay. So if I look back at my chart and I think about that, what would that be? It would be an E, right? So if you think about that, a 10 is an A and a 15 is an F, then a 14 would be an E. Okay, let's do the next one. All right, so this time I've got a 1, 0, 0, 0. That would be an 8. And the next one's easy because it's also an 8, right? So we can go ahead and bring that down. So this is my 16-bit hexadecimal number, 88E5. This is the way that you'd represent it. You would have a 0 and an X, lowercase x, 88E5. You can also represent it like this, 88E5 base 16. What does that break down to in octal? I'm not going to go through here and do this, but I'm going to give you the value and then see if you can compute it over, because all that you have to do is break it up into 3s, right? You can do that, but here's what it equals. See? It's 104, 345. the same as what we had on the last slide. Huh, okay. So then that equals 35,045 in decimal or base 10. So if I look at these numbers, what do I see? If I'm writing code in numbers all day long, I can write it in binary. Ooh, yuck. I could write it in octal. It's a little bit better. If I write it in decimal, 35,045, that doesn't directly relate to the bits, right? So it's still, you got to figure things out. You got to break down the math. It's a lot harder. But if I deal with it in hexadecimal, look how it's much easier to say an 8 has a pattern of 1000. An E has a pattern of 1110. A 5 has a pattern of 0101. Those patterns are much easier to see in your mind and visualize if you're dealing with more of a binary system. You're trying to get down to understand the ones and zeros. All right, so you ever wonder where you'll ever use hex? You're probably sitting here and you're going, why are you teaching me this? Why do I need to care about hex? You're ready? You use it every day. What do you see? I see white on the left and I see black on the right. These color codes, ready for these color codes? White is F, 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 F. Black is 00, 00, 00, 00. Those are hex. Did you know that? You are doing style sheets for colors in hex. Yep, that's right. You're using it every day and you didn't even know it, I bet you. I bet you right now you're going, oh, I didn't know that. Well, a few of you might know it, but the point is you're using hex every day. So therefore, knowing how to break that number down gives you a little bit more information. If you're going to really excel and have that technical expertise in this business, these are the types of things you need to know. So let's bring down the first F. So here's an F. What is the binary equivalent to F? Not sure. You can go back. I hope that you wrote it down. An F is a 15, and a 15 would be equivalent to having all ones. Well, okay, that's pretty easy. So let's bring down the next F. Yep, same thing, all ones. F, F, F. That is the binary equivalent of the color white. There it is, all ones. See that? How would you like to write that instead in your CSS? Oh no, that would not be too fun, would it? I think it's easier to write the Fs. So this equates out to a base 10, which is decimal, to 16,777,215. That's your base 10. See that? How about an octal? So an octal is a base 8. So 7 would be 111. So it'd be sevens. All sevens all the way across. So you can see that the hex code system is much easier to deal with. Also, if you had to write base 10 for that color, wouldn't that be kind of a pain too? I mean, it's much easier to write your color codes in that FFF series than it is to write 16,777,215. So what are practical uses for hex? Well, we just went through color codes, right? Another one are error messages. Another one that I did would be for barcoding. So identification systems can be in hex as well. We want to communicate with particular APIs. There are times when you have to communicate via either octal or hex. It's not always just going to be in a decimal system. Sometimes things are encoded in hex. So what are some of our takeaways? Hex or hexadecimal is a more condensed notation. It's easier to read. It allows up to 16 digits, 0 through 9 plus A through F, capital A through F. One hex notation is the same as a 4-bit groupings in binary. It's useful for larger numbers. Color codes use hex. So therefore, you're using it every day. Get to know it. Get to know those 0 through 9, A through F. And once you do, it's going to stick with you and you'll be able to understand binary so much better.